Today we're going to be discussing ice tables. Ice tables are used throughout the 1160 course, and your understanding is essential to your success. First, let's review the core information required to understand ice tables and their uses. You should know that strong acids completely dissociate in solution, while weak acids only partially dissociate in solution. If we are given a 0.2 molars of HCl, which is a strong acid, we know that we are going to end up with 0.2 molar of hydronium ions due to its complete dissociation. But if we are given a weak acid that only partially dissociates, to what extent does that occur? We can use an ice table to determine the production of hydronium ions from the weak acid. From this, we can then calculate the pH of the weak acid. Let's do a problem to determine the pH of a 0.2 molar HNO2 solution. First, we must recognize that HNO2 is a weak acid. It is critical that you memorize the list of strong acids in order to differentiate between the two. Now that we have determined this, we can write our equation. HNO2 plus H2O leads to H3O plus NO2 minus. When writing the equation, remember the role of an acid, a proton donor. The weak acid reacts with water to donate a hydrogen and create hydronium ions, decreasing the pH of the solution by making it more acidic. Now that we have confirmed it's a weak acid, we can set up our ice table. We know that the initial concentration of our HNO2 was 0.200 molar, with our liquid not going to have a value in the ice table because liquids and solids aren't included. And then our H3O and NO2 minus are both products. At the beginning of the reaction, the values are going to be 0. Now let's consider the change. Change in the initial concentration is going to decrease by a value of x. We're going to use x because we're not sure how much it's going to decrease yet. That's what we're calculating. While the hydronium ions are going to increase by a value of x, and so is the NO2 minus. Now we've made our initial and our change columns. We can sum them to find our equilibrium. 0.200 minus x, x, x. Now that we have our equilibrium values, we can create a Ka expression and plug them in. Ka equals products divided by reactants raised to the power of their coefficients. So Ka is going to equal x times x divided by 0.200 minus x. We can simplify this by writing it as x squared divided by 0.200 minus x. Now we can plug in the Ka value, which was given above. It was 4.6 times 10 to the negative 4th equals x squared divided by 0.200 minus x. At this point, we should realize that with such a small Ka value, we can make the approximation that x is small and can cancel it out. This means that the change in the initial concentration is so small it is considered negligible. This can later be confirmed. So from this point, we can solve for x. We'll multiply by 0.200, canceling that out. Multiply this side by 0.200. And we will get 9.2 times 10 to the negative 5th equals x squared. From here, we're going to do the square root, and we find that x equals 9.6 times 10 to the negative 3rd. Now we can verify that the approximation that x is small is valid by dividing it by the initial concentration and multiplying by 100. So 9.6 times 10 to the negative 3rd divided by our initial 0.200 times 100 equals 4.8%. The approximation is valid if the percentage is less than 5. This approximation is valid even though it's barely so. Throughout this, don't forget what x represents, the hydronium ion concentration produced. That means we use this value to calculate the pH of the solution. we know that the pH equation is pH equals the negative log of the hydronium ion concentration, which we just found above. So we can plug these values in to see that pH equals the negative log of 9.6 times 10 to the negative third. By plugging this into your calculator, you'll find that the pH equals 2.02. If the x's small approximation is found to be invalid, you must determine the value of x without canceling it out. This can be done using the quadratic equation. Ice tables can also be applied to weak bases and their pH calculation, where you'll be determining the hydroxide ion calculation by finding x and then plugging that into your pOH equation to determine the pOH, which can then be used to find the pH, where pOH plus pH equals 14. It's important that you understand these equations and their relationships in going from one to the other. I hope that this video was helpful.